Hello, I'm your teacher Terry, and I'm going to go through the three types of intermolecular forces in a little bit more detail. Hello, I'm your teacher Terry, and in this video I'm going to go through the three types of intermolecular forces in a little bit more detail with you. The first one is the London-Dispersion forces. Please check out my last video if you haven't on introducing the three types of intermolecular forces for neutral compounds. And this is attraction due to temporary dipoles by electrons moving around by asymmetrical electron distribution. That's what it means. And every single atom and molecule, every molecule exhibits London dispersion forces. And here we describe which ones are stronger or weaker, that sort of thing. And what we find as the molecule becomes larger, the London dispersion forces increase. Okay, so it increases with molecular mass and size. The greater the molecular mass, the bigger the molecule is, the greater its London dispersion forces. And that's simply because there are more electrons and more area in order to attract. If we look at methane here, methane's quite small. Methane's quite small, so this is only a small amount of surface area for it to create attractions with other molecules. With ethane, we have, so ethane is CCH3, CH3, and if we look at that with another CH3 molecule, there's a CH3, CH3. We see more attraction, more surface area that can attract. Again, as we get larger, we now have 4 carbons. I'll draw the line structure here. Just so 1, 2, 3, 4. 1, 2, 3, 4. We have even more potential surface area for intermolecular forces. This is like spaghetti. So if you have long spaghetti noodles, it's harder to pull them out of the pan or the pot because they're all stuck together and intermingled together. If the spaghetti is shorter, it's easier to take it out of the pot. And similarly here, the stickiness between the noodles, your spaghetti noodles, is more significant if your noodles are longer compared to if they're shorter. But then if we look at branching, so these compounds both have the same molecular mass, same molecular formula. So it's propane, dimethylpropane. So there's 5 C5H12. And yeah, is that right? 1, 2, 12. Good. And here it's a branched. So this one looks like this molecule. A carbon in the middle with these 4 ones around. It's like these are kind of like balls, these two here attracting to each other. But here, all 5 carbons are in a line. 1, 2, 3, 4, 5. 1, 2, 3. So look at the surface area. Significantly more surface area. 1, 2, 3, 4, 5. 2, 3, 4, 5. So we could have greater attraction. And every time we increase the surface area, we can increase the attraction. So less branching increases the intermolecular forces, and more branching decreases the surface area, which is going to decrease the intermolecular forces for them. Okay. For our next one here, London dispersion, or dipole-dipole attraction, it really has everything to do with molecular polarity. So the polarity of the molecule as a whole. So if we look at this, ethyl methyl ether, we have a dipole moment pointing towards the oxygen, where each carbon points towards the oxygen. So the net dipole moment is going to point down in this molecule. And this ether has a dipole moment, dipole of about 1.22 Dubai. It has a boiling point of 11 degrees Celsius. And for our last one, hydrogen bonding. Here, it's just like a review. Check out the last video if you're not sure what this is. But it's essentially, it's like a dipole-dipole attraction that's very strong. We can draw delta negatives on the nitrogen or oxygen or fluorine as long as it's bonded to a hydrogen. And then the hydrogen is always a delta positive. And these are polar bonds. They're quite strong, but they're much stronger than a normal dipole-dipole moment. So we call it hydrogen bonding. And if you see over in the corner here, I have these water molecules, and we have these intermolecular forces to the attraction between the molecules of an oxygen of one molecule, hydrogen of another molecule. And because the hydrogen's bonded to an oxygen, this is a very strong intermolecular force. This is the strongest one that we have. Now you may be wondering, why does the hydrogen have to be bonded to oxygen, nitrogen, or fluorine? And this is a little diagram from the OpenStax textbook where it's a graph that should give some empirical data of it. So this is a graph, and on the y-axis here, the vertical axis, it's boiling point. So this shows the temperature of which the compound can boil. Okay, so this is boiling point. And then here is the period. Okay, so it's the period of the periodic table. Here's a periodic table right here. And so I just kind of move things over a little bit. So we talked about the boiling point. This is the period here. If we look at second period, we see there's nitrogen, fluorine, and oxygen, and all of those are on the second period here. So these points, each point is a compound that's of an element that's bonded to hydrogen. So here we have nitrogen bonded to hydrogen. These are all the second period elements bonded to hydrogen. We have nitrogen bonded to hydrogen, and then fluorine bonded to hydrogen, and then oxygen bonded to hydrogen here. These are all second period elements bonded to hydrogen. Here we have third period elements bonded to hydrogen, so phosphorus right here, and then chlorine is here, and sulfur is here. So we have three third period elements bonded to hydrogen, and then the fourth period elements bonded to hydrogen. Here's selenium, arsenic, and bromine. So we'll go to the fourth period. Selenium, arsenic, and bromine. All of these are bonded to hydrogen. And then here's the fourth: tellurium, antimony, and iodine right here, bonded to hydrogen. So it shows the boiling points of each element as in its the compound bonded to only hydrogen, and compares the two. If we look at the second period, we see that the element is, if the hydrogen is bonded to an oxygen, a fluorine, or a nitrogen, the boiling points are significantly higher compared to any other element within the group. So if we follow this blue line here, this blue represents the oxygen family here. So hydrogen's bonded to oxygen, and then sulfur, selenium, tellurium. Right here, oxygen, selenium. So we're going down a group. Oxygen bonded to hydrogen significantly higher, right? Significantly higher because we have strong hydrogen bonding with oxygen, but not so much hydrogen bonding with sulfur, selenium, and tellurium. It's quite muted. Same thing with the halides. So we see HF has a strong intermolecular forces compared to the other halides in that group, chlorine, bromine, iodine. We have not as much, and then same with nitrogen. So whenever hydrogen is bonded to a nitrogen, fluorine, or oxygen, we have strong intermolecular forces, sort of bucks the trend that we normally see. And then what about these three? If we just look at these look like they have their own trend. If we ignore the hydrogen bonding, right, of the oxygen, fluorine, and nitrogen, and we see that as we go down a group, right, as the period gets higher and higher, so we're going down a group from sulfur to selenium to tellurium, sulfur to selenium, tellurium. We're going down a group. The boiling point increases, which means the intermolecular forces increase as well. And intermolecular forces in this trend increase because of molecular mass. We have stronger intermolecular forces, and because the stronger uh, uh, London dispersion forces. What am I saying? We have stronger London dispersion forces, so we have more mass, which is why it's increasing like this. Same thing with these groups here. As we go down a group, we see the intermolecular forces. The London dispersion forces increasing, which is why we see the intermolecular forces increase. So this trend, as the mass increases from compound to compound, the intermolecular forces increase, so the boiling point has to go up. And then here, these three are separate from the trend because they exhibit strong hydrogen bonding. That's why we see such a higher boiling point, which represents a higher intermolecular forces compared to the other ones here. One thing I just want to point out as well, if you look at the trend between, say, HCl, HBr, and HI, this goes opposite to what you would expect for a dipole moment. So HCl has a stronger dipole moment within itself. The electronegativity difference between hydrogen and chlorine is a lot stronger than hydrogen and iodine. Yet, even though HCl is more polar than HI has greater intermolecular forces. It's less polar, but its intermolecular forces are stronger. So the dipole-dipole intermolecular forces for HI are less than the dipole-dipole intermolecular forces for HCl. However, the size overrides that. So the London dispersion forces are higher for HI because it's that much longer, or it's that much larger, which supersedes the dipole-dipole interaction of HCl and HBr. So that's why we also see the trend like that. All right, so that's it for intermolecular forces, for introducing them. We're going to go on to some practice problems. Hope you enjoyed it. See you in the next video. Cheers.